Dear students of third year A3MA, A3MB, I would like to welcome you to the new academic session 2020-21 and also to this course Fluid Mechanics 2 MEC 3310. As you are aware, the teaching in this trying and testing times is going to be via the internet or the online mode, and myself, Dr. Nadeem Hasan, and Dr. Syed Fahad Anwer would be taking this course in this mode. As far as the method of engaging you all for this course is concerned, we will be systematically uploading the lectures in the form of PowerPoint slides, where I will be explaining the different slides through voice or embedded voice, you can say, and then we will be supporting these PowerPoint sort of lectures with embedded audio, with PDF lecture notes, with they will also be uploaded. And as you are probably also aware, you might have received the link to join the Google class for this course, and I was told by Dr. Anwer that already many students have joined the class, so that's good. And the class will be used to have any kind of discussion with the students. Their queries, their doubts, all those things can be posted in the classroom and we can respond to them. And so the whole class is getting managed through that platform. Now, I will be taking roughly around 24 lectures for my portion of the syllabus, and the remaining 24 lectures will be taken by Dr. Anwer. So I will be starting the course. So the first 24 lectures will be conducted by me. Now we are going to start this with a very basic introductory lecture, where I intend to cover three basic sub topics, you can say, as I've listed in the contents. I'll give you a brief introduction to the course, that is its objectives and what we aim to achieve through this course. And as a motivational sort of exercise, I will discuss the far and wide-reaching role of fluid mechanics, not only in technology and various processes that you normally study in engineering, but also related to any kind of natural environment in which we live, and even sustaining different life forms, examples from biology, things like that. So role of fluid mechanics is just intended to give you the far and wide reaching sort of applications of the knowledge gained in the courses on fluid mechanics. Lastly, I will conclude this introductory lecture by connecting you with your existing knowledge of fluid mechanics that you have gained in the earlier course on fluid mechanics, that which was in second year, MEC 2310, Fluid Mechanics 1. So I would like to connect to that and would also point out how we plan to extend that knowledge. Okay, so that knowledge, though, is very essential and it's like a base for us, but is not sufficient for it to be able to deal with any fluid flow problem that engineers or applied scientists or technologists may face in real world. So we would like to extend that knowledge through this course. So this is about the contents of my today's or this lecture 1, you can say. So I will move on to the next slide discussing the objectives of this course. Okay. Right, so moving on to course objectives of our course Fluid Mechanics 2. The first objective, if I may read it, to be able to model, express viscous fluid flow using basic physical principles. So this objective is very self-explanatory. It says that we would like to see how we can develop the governing equations for any kind of a viscous fluid flow using basic physical principles. So this is our first objective. These objectives are just a little bit reworded to make them more clear from the point of view of my lecture. These are essentially the same that you will find on the departmental page where the syllabus of this course is given. You are expected to download that syllabus page where the course objectives and syllabus and reference books all are given. So you will find that these, by and large, these 5 objectives, a little bit, you can say, not exactly in the same words, but the meaning is the same. You will find these objectives written down there. Okay. Now the second objective, to develop an understanding of viscous flow behavior by examining solutions to well-known classical problems. Now what does this mean? In the first objective, we are trying to look for basic equations which govern viscous fluid flow, and we would be searching them using basic physical principles. Now once we are in a position to write those equations, the equations in general will have different types of terms. You may already have seen one of the equations like in the form of Euler equation in your earlier course. So Euler equation has got a number of terms on the both the sides, like pressure forces, body forces on one side, and convective accelerations and local accelerations on the other side. So these type of terms are there in these equations, and I'm just not talking of one equation, but as you will see, there will be a set of equations which will together model any viscous fluid flow. So all those physical meaning of various terms and all those things, they provide you the feel of how viscous flow behaves or is going to behave rather. So that we would like to examine those things by looking at solutions to some well-known classical problems. Now, like in any subject, the same is the story with fluid mechanics. There will be some classical problems like flow in pipes, flow between two concentric pipes, or flow between two concentric cylinders, or in channels and things like that, simple geometries where of course you can obtain solutions to these basic equations of viscous fluid flow. So those are known as classical problems. They are discussed in detail in most books on fluid mechanics. So we will be examining the solutions with the dual purpose. Okay, the first purpose would be as listed in this second objective, understanding of viscous flow behavior. That is the main line here in this second objective. And the third objective is also connected with the second one, particularly by examining solutions, this keyword that is written in second objective. The third objective says development of relevant mathematical skills of approximation and analytical solution for viscous fluid flow problems. It means that when we will be examining solutions to well-known classical problems, in the process we will also develop skills, mathematical skills, where the art of approximation and how we can go about solving the equations to get a analytical solution to a viscous fluid flow problem. All this will be you will be exposed to all these things. Okay, so this is the third objective. Now moving on to fourth objective, development of an understanding of important fluid flow phenomena. So these are very much real fluid flow phenomena that we observe, like formation and evolution of boundary layers. So this is a new term. In a nutshell, if I tell you at this stage, I can simply say that when fluid flows over any adjoining solid surface, usually it forms a very small thin layer where the effects of viscosity are very, very dominant, and this leads to a lot of fluid friction effects close to any solid surface, and you will learn more about it in due course of time. So this is this thin region forming adjacent to any solid surface, having very high shear and viscous effects, is what is termed as a boundary layer, just to explain at this stage. So we have a specific objective of learning how to tackle this phenomena of what is the physics behind formation of boundary layers, and how they evolve, what are the characteristics, and what importance they have from the point of view of engineers and various applications where engineers will be engaged in design. So this is the fourth objective. Now moving on to the last objective, which is dealing with the turbulence, the topic of turbulence in fluid flows. And so we will be aiming to give you a very brief, you can say, introductory type of a series of lectures where you will understand and appreciate the challenges and difficulties of tackling turbulence in fluid flows. And we will also try to impress upon you that the engineering approach of tackling turbulent flows is to take a statistical approach. Okay, and what is the need for that from the point of view of engineers, that we will be going through in this course. But we will not be taking you to the actual concepts of detailed you can say turbulence modeling or things like that. Those things are typically taken up in dedicated courses or elective courses, okay, and not in a course like what we have now, Fluid Mechanics 2. So these are my to summarize, these are my 5 objectives, and yes, now I will be moving on to the role of fluid mechanics in the next slide. So moving on to role of fluid mechanics in different domains. I have listed here sort of 4 categories, put every kind of conceivable application into 4 categories. This is not exhaustive. You can come up with something which is not listed here, but the idea is to by and large talk about a very vast sort of spectrum of application of fluid mechanics. So the first is the technology and various processes that we normally study in engineering courses, specifically even even mechanical engineering courses. So you can see I have listed them as power generation technology or equipment and processes related to power generation. So you can recall you might have done some thermodynamic analysis of steam and gas turbine power cycles, or so these particularly the steam and gas turbines and even wind turbines, and so all kinds of these turbines, they rely on the fluid flow through them as they extract energy from the moving fluid. So fluid flow processes obviously play a very important role in their design and in their performance and so on. So next we move on to something again very obvious. Any design of any system or vehicle that is a transport system or a vehicle over lands, air or sea, it will naturally involve interaction with either the atmospheric air or the water in the seas or the ocean, and even any kind of a transport system on land or terrestrial transport system. It will also be moving surrounded by the atmospheric air. So all these systems, they are from the external aspect, they are exposed to interaction with some kind of a fluid. And as you all know, the fluids, they will interact in the form of forces, and you need to be properly able to account these forces to design these systems and vehicles. Moving on to internal combustion engines that you normally have for your automobiles, your bikes, your any kind of you can say fossil fuel driven land transport vehicle. So IC engines, what is the role of fluid mechanics there? In these engines, there are a lot of processes, gas exchange processes, intake and the exhaust, and then even inside the cylinders, you have mixing and charge motion, and apart from combustion, which is also a fluid flow process, but probably lesser role of fluid mechanics there. But in the gas exchange processes and mixing inside the engine cylinders or the manifolds and things like that, there the fluid mechanics play a very vital role. And moving on to propulsion systems, in the context of again transport vehicles in the sea, maybe ships, maybe underwater submarines, and these days we talk of even autonomous vehicles, and for air you obviously have the aircrafts and even your missiles, which are weapon delivery systems, and so all these systems, they will have some kind of a propulsion system which generates force to move it. Okay, so these propulsion systems typically for aircraft are the jet engines, which have their different components, and the exhaust is through nozzles which generate high speed stream of fluid which is being ejected out, which generates the thrust. And similarly, even for rockets, you have a nozzle which expels gases at a very high velocity in order to generate the relevant thrust. So fluid mechanics again at the heart of these propulsion systems. Even propeller based systems that we have for ships and submarines, there also the propeller moves in the fluid, and the interaction between the fluid and the propeller generates the required thrust or the force. Next, we move on to something not exactly related to mechanical, but definitely civil engineers would be very much involved in the design of earth fixed structures. So these are structures that could be bridges, tall buildings, towers, bridge piers, and things like that, which are exposed to flow of air around them. And again, for stability and of these structures and safety of these structures, you need to consider the forces generated by the moving fluid around them, so that you design them in an appropriate manner. And next we look at systems which are designed to transfer heat, not just by conduction, but by convection, where some fluid flow is involved in carrying the heat from one location to the other. And the removal of heat, as you are very much aware from many examples, like you put coolants in your engines, IC engines. So the coolant is like it moves through a circuit. So the fluid flows through a circuit and removes heat from the hot components or parts of a system. And this heat removal, every day we experience this from our own bodies also. And for example, in summers we generally don't feel comfortable if we are not sitting beneath a fan or sitting in an air conditioned space, which is basically causing a certain flow of fluid over our bodies, whether it is controlling the temperature and humidity in case of air conditioners, or it is simply moving the fluid in the case of fans. But the idea is that fluid motion over our bodies helps in removal of heat and make us feel more comfortable. Transport of fluids is another simple application, like a typical urban water distribution network, where pipes are used to transport water over large distances. Extreme examples are transport of oil over large distances, refineries to refineries, and things like that, and even bringing such gas, you can say, from very large distances, from the drilling sites to the target or the where the usage is intended. So transport of fluids is a very basic problem. You want to send fluid from one location to another location based on its source and intended usage. So you need to transport it through specially designed pipes and ducts, and you have to use related machinery like pumps, etc. So this is we are now ending the list of technology. Last and but not the least, it is interesting to know that fluid mechanics also plays a lot of role in various you can say sports. People who are aware of and they watch cricket a lot and are aware of swing of a cricket ball. Let me tell you that swing is a very complex and interesting phenomena, and it involves boundary layers forming on the cricket ball. That much I can say at this stage. So this is one example. Then the flight of a badminton shuttlecock, the curving of a football or baseball, all these things, though the players probably don't know the detailed fluid mechanics behind it, but they seem to exploit all this to their advantage. So this would be where I would be just stopping discussing the technology and moving on to the environment and geophysics related applications. There are a lot of fluid flows taking place in the atmosphere and in the ocean, and these fluid flows influence weather patterns. They are responsible for understanding the behavior of you can say thunderstorms, how they form, where they are likely to form. So they serve as fluid mechanics. Knowledge of fluid mechanics serves to create a sort of a not only the understanding but the safety for various you can say flights and different the air traffic management in the Earth's atmosphere. We can have an understanding and issue warnings of dangerous weather patterns forming in different zones. So some of the examples of dangerous weather patterns are hurricanes, tornadoes, cyclones, and their formation and evolution is very much a fluid mechanics phenomena. Now moving on to a more relevant problem of having a more sustainable planet. You must have heard about pollution, not only in the atmosphere but also in water bodies. So how a pollutant mixes with the air or with the water bodies and how it eventually spreads is again a fluid mechanics problem and has to be studied using fluid mechanics principles. And another very interesting fluid mechanics phenomena that goes on right inside the Earth's core, where you have got molten ionized fluid, is a lot of convection goes on there due to thermal gradients and the gravitational effects combined, and the rotation of the Earth. These three things combine to generate a lot of convection in the Earth's core, and this convection is believed to be the dynamo which generates the magnetic field of the Earth, and which is so important for many other phenomena. So the magnetic field of the Earth is connected to convection in the Earth's core or fluid motion in the Earth's core. Now the biological systems, so life-sustaining fluid mechanics processes like in the human body, the respiratory and blood circulatory systems, which are one of the most vital systems for sustaining the human system, biological system. They are fluid flow processes. Apart from this, there's also a fluid flow process in the brain, the cerebrospinal fluid in the brain, that also undergoes a process of motion, not only in the brain but comes right into the spinal cord and serves to act as a lot of, you can say, a shock absorber for your spine as well as the brain. So it absorbs a lot of shocks, and this is another example of fluid flow in the important fluid flow in the human body. And lastly, just moving out of the terrestrial domain, I would like to briefly mention some astrophysical processes like convection in stars, stellar convection, this is known as. And again, this is because of the stars are mostly conglomeration of gases, and because of the large amount of heat and the energy that is being generated in the stars, the heating and again the gravitational effects and all these are the dominant causes of convection in the stars. So stellar convection, which is again important from the point of view of the birth and life cycle of a star. The explosions, the supernovae explosions, before the death of a star, this star continues to grow and expand, and then um, ultimately experiences when the rate of expansion becomes very high and gravity is unable to um, control it. So there is an explosion which you call as supernova explosion, and the explosion expels the gases and matter at a very high rate. So again, a fluid flow process. And astrophysical jets. So again, ejection of uh, gases at a very high rate um, in the astrophysical domain. So without going into technical details of these, this is just to give you a motivation and make you aware of such a far and wide-reaching spectrum of fluid mechanics knowledge, where fluid mechanics plays a very important role, and its knowledge also is important. So I would like to end here itself and become more specific and start moving towards your course, fluid mechanics 2. So moving on to our putting the fluid mechanics into perspective in relation to different mechanics courses that we go through in mechanical engineering. So I'll move on to that after this. So the various courses of mechanics in mechanical engineering that you typically go through, they can be related in a sort of a tree, a mechanics tree diagram that I have shown here. At the top, sitting at the top is a heading which I have given classical mechanics, which I have broadly split into two categories. One is rigid body mechanics. This is, as the name suggests, in this branch, we study the effects of forces on material objects, assuming the objects to be rigid. That means their deformation effects are not considered or considered to be negligible. So this is what we term as rigid body mechanics. So this branch, typical courses or their portions you have been studying right from let's say class, even from school days, and in typically classes beyond 10th, 11th, 12th, you have studied rigid body mechanics. And in first year engineering, you have gone through a rigorous course in rigid body mechanics, where more realistic approach towards application of rigid body mechanics was adopted in the form of two and three dimensional world problems involving complex connections and supports. Next, the other side of the story is opposite to rigid body is mechanics of deformable media. As the name suggests, here the effect of forces is such that not only there is motion involved, but there may or may not be motion involved, but deformation is an important effect in this branch of study. So, mechanics of deformable media. This we can further split into two types of approaches to study such mechanics of deformable media. One approach is that of what we call as the continuum mechanics, and the other is, of course, taking into account the discrete nature of matter through molecular or statistical mechanics. Now, in continuum mechanics, we disregard the events taking place at the atomic and molecular level. Rather, we don't regard matter as comprising of these discrete entities. We simply assume it to be a continuous distribution, and with proper justification, of course, that we will discuss when we will formally study our fluid mechanics. You might have been told about those basic ideas and assumptions of continuum mechanics in our earlier course on fluid mechanics. Also, they apply to solid mechanics. So, continuum mechanics courses in mechanical engineering are typically or split into two categories: solid mechanics and fluid mechanics. In your curriculum, we have two courses on basic fluid mechanics, and there's a third one on applications in fluid machines. So you are already you have done one course in fluid mechanics, and you're about to embark on the second one. Solid mechanics also, you might have done a first course in solid mechanics in second year. Now, what is the fundamental difference as far as solid and fluid mechanics is concerned? In solid mechanics, when the external force or forcing is within a certain limit, typically you can say elastic limits, the deformation is always finite. That means it doesn't continue in time. If you apply a certain load or force on a solid, then it will deform within the elastic limits. It will deform according to its elastic law, and deform up to a finite amount, and that's it. The deformation stops. Now, in the case of fluids, it's quite different. The deformation is continuous in time for even the smallest level of forcing. This is very interesting, that however small is the force, particularly the shear force, you might have been told about this as a this aspect of fluids is often taken to be one of the defining characteristics of fluids. That fluid is a substance which deforms continuously in time for even smallest level of forcing. So naturally, in case of fluid mechanics, since the deformation is continuous in time, you don't work with the deformation as a physical entity, but rather you talk of deformation rates, because since it is continuous in time, it is the rate which is going to dictate the things, and not the actual amount of deformation. So this is what I call as the mechanics, the whole umbrella of mechanics courses that you typically have. And apart from molecular statistical mechanics, I believe in your mechanical program you are exposed to all of the other types. So this is where we stand as far as the courses in mechanical engineering are concerned related to mechanics. Next, we move on to what we have here. We would like to recap some things, the key or the main things that we learned in our earlier course in fluid mechanics, so that you are able to connect to what you already know, and how are we going to extend your knowledge in the subject of fluid mechanics. So let us now go through a quick recap of the main ideas that were learnt in fluid mechanics 1. The first and the foremost thing regarding any continuum mechanics course is the fundamental idea of treating the medium as a continuum. So fluid is a continuum, and what we mean by continuum is that we disregard its discrete nature, because we know that all matter is discrete eventually at the atomic and molecular level. So the processes at the atomic molecular level are basically disregarded in a continuum treatment. Rather, we treat it as a continuous distribution of matter, and you can think of a continuum which actually helps a lot in as far as my own experience goes with the subject, the notion of a fluid particle actually. So at each point in the space occupied by fluid, if you treat it as a continuum, you can think that at each point there are tiny point-like particles, which we just to name them, we call them as fluid particles. They are nothing but they are so tiny that you can effectively treat them as a point. To give an example, if I just consider, let's say in a typical room in which you are sitting, you have air, and it is typically at 1 atmosphere, and typical temperature would be, let's say, 30-35 degrees. So at these conditions, around 30 degrees and 1 atmosphere, you can use your kinetic theory of gases, or the theory that you've learned for gases, that what is the amount of density of atoms and molecules at such states, at such pressures and temperatures. So if you calculate the atomic and molecular density, then it is possible to answer this question, that how many atoms and molecules of air are expected in a 1 millimeter cube volume. If you do the calculations, it turns out that approximately 10 to the power 8 or 9 such large number of atoms and molecules you will find in such a tiny volume of space, 10 to the power minus 1 millimeter cube, or rather 10 to the power minus 10 to the power minus 3 meters cube. So 10 to the power minus 9 meters cube. 1 millimeter cube is equivalent to 10 to the power minus 9 meters cube. So 1 millimeter cube in a, let's say, a typical size of a room is virtually like a point. Okay, so I call these fluid particles as tiny point-like entities, which is indeed very small, and you at each point you can think that there is a particle. Okay, so when you think of a fluid, it helps to think of the fluid as a collection of virtually infinite particles, fluid particles, each particle instantaneously occupying a certain position in space. Okay, so this is what the notion of a fluid particle is. Now moving on to surface and body forces. These are very fundamental force models for continuum fluid mechanics. What are these surface and body forces? Well, in a fluid, if you imagine any surface, then fluid on either side of the surface would be engaged in force interactions through the surface. And from the point of view of atoms and molecules, though we are not considering them or their effects, we can say that the origin of these forces are basically lying in the exchanges of momentum at the atomic and molecular level through the surface, and the force potentials that exist at the atomic level. So those atomic entities, momentum exchanges at the atomic level through the imaginary surface in the fluid, and the force potentials, they can all be lumped up and just talked about as a surface force at any point in the on the surface of or an imaginary surface in the fluid domain or fluid continuum. So this is what is a surface force. Body force, as you have been told, they are due to external force fields, and the most common force field that we know, which every matter experiences, is gravity. So that is one example, but not the only body force. For example, I talked of convection in Earth's core. So there it's ionized molten liquid or gas. So the ionized the ions can experience electric and magnetic fields also as a body force. So body force, remember, it is caused by external force fields. Okay, they are imposed on the fluid. Okay, so they may get influenced by fluid motion, but their origin is not related to the fluid motion. They are because of external force fields which are present, like gravity and as even electric and magnetic fields for suitably charged or ionized fluids. So this is what is the concept of surface and body forces. Next, we went through the knowledge of fluid statics, where we examined the state of stress and showed that it is isotropic, and value is same if you have a small area at any point, and you just rotate the planar area or surface in the fluid at a fixed point, then it keeps experiencing the same normal stress, and that normal stress is what you call as the fluid pressure. So the ideas of pressure and the related hydrostatic equation, which talks of the variation of fluid pressure in a stationary fluid, which is basically caused by body forces. And then you had applications of manometers and pressure measurement and forces on submerged surfaces, and even relative static equilibrium for the case of accelerating containers and all. So those were ideas related to fluid statics. Then after statics, we naturally moved on to kinematics, and there we learned what is an Eulerian and Lagrangian two frames of reference or two viewpoints for describing the motion of fluids, because kinematics typically deals with describing the motion in terms of velocities and accelerations and all. So there are two fundamental viewpoints, the Lagrangian being the more natural one, where you focus on our smallest entity, which I have defined earlier, the fluid particle. So if you focus on a fluid particle and follow its motion or track its motion, then you are essentially adopting the Lagrangian viewpoint. And whereas if you talk of all fluid particles in the fluid, if you take them together, so actually they are infinite, but you can talk in terms of their spatial location. So at each point at a given time, there is always a fluid particle. So if you take this holistic viewpoint, this is also known as the Eulerian viewpoint or the field viewpoint, and you describe the velocity field, and you say that this is how velocity varies in space and time. So meaning is that if you are at a fixed location, then as the fluid particles arrive at that point at different instants of time, what are their velocities? Or if you fix yourself in time, then at different points if you visit at a given time instant, like a camera snapshot of the fluid, then those velocity variations you can readily express as from Eulerian viewpoint. So velocity field itself is a Eulerian variable. So that is what the essential idea that we had learned from our earlier course. Then we did go through some interesting flow visualization tools. We talked of streamlines, path lines, streak lines, timelines. I need not talk about their definitions at this moment, but you must be remembering these terms. So these are useful tools for visualizing the flow fields. And visualization plays a very powerful role in understanding fluid motions, because you can actually talk about the directions and how the fluid particles are moving in space, and you can physically feel the fluid motion, because most of the time, except for liquids, when you talk of air flows and all, they are difficult to see. Okay, so even liquids also, you don't actually, you just see the whole fluid as a whole moving, but it is difficult to visualize the local Eulerian velocities and all. So these visualization tools are particularly helpful. Some of them helpful in mathematical sense, like streamlines and these streak lines, and while timelines and path lines, they are also very meaningful for carrying out physical experiments with the fluid flows. Even streak lines you can easily generate in experiments, but streamlines, they are virtually very difficult. In fact, you can only talk about them mathematically, or maybe you can generate them from these days with the help of computers, if the velocity field is known. So you can generate them through either in your simulations on a computer, or you can just obtain their equations analytically and visualize them on a paper. But in physical experiments, path lines, streak lines, timelines are readily, you can say, constructing them is possible. Now moving on to the third very important kinematic concept that you already have, and that is that of a material derivative of any property associated with a fluid particle. Now this is very important because from the point of view of application of physical laws to a particle, because whether it's mass conservation, Newton's second law of motion, which you also call as momentum equation, or maybe even thermodynamics laws, when you apply them to a particle, then these laws naturally involve the time rate of change of certain property of that particle associated with that particle. So that time rate of change of any property associated with a fluid particle is what you call as the material derivative, and we can express it in terms of Eulerian fields that we already know. Then to move further, we did some inviscid flow dynamics with the help of Euler and Bernoulli's equations. We later on moved to finite system and control volume analysis in that course, and in control volume analysis, we learnt an important principle by the name of Reynolds transport theorem, and there were a lot of application oriented examples where Reynolds transport theorem and physical principles were combined to obtain control volume equations of mass conservation, then momentum equations and all, and you can compute some quantities of engineering interest, like gross quantities like total forces as the fluid moves through a certain finite volume or a region in space. Then the surroundings would exert some forces and all, so those can be easily computed using this approach. But remember, a finite control volume analysis approach requires knowledge of velocity and various fluid properties on the control surface and inside. So it assumes that you know these values, but these values are only known if you perform a detailed fluid flow analysis to obtain information about this, which is what we would be learning in this particular course. What governs the detailed flow behavior in a nutshell. So this is important from the point of view of connecting what we already know and what we are about to learn. And to conclude this quick review and recap, whatever control volume analysis, finite system analysis you may call, whatever we learned, we also showed you some applications of that in studying some flow phenomena using CVA or control volume analysis. And specifically to name some flow phenomena, you went through viscous pipe flow analysis, fully developed flow, of course, in the earlier course, and related energy losses in pipes. Then we also showed some interesting usage of the finite control volume analysis to study quasi 1D, to develop rather quasi 1D models for inviscid compressible flows with applications to nozzles and diffusers. And of course, a very important concept in compressible flows, that is formation or the analysis of shock waves, or sort of, you can say, normal discontinuities to flow paths or streamlines. These shocks, so to speak, normal shock theories, so can be derived again using a control volume approach. So all this was done in Fluid Mechanics 1, and this is where I would like to just end my discussion on a quick review of what we learned in Fluid Mechanics 1. This is not, as I've said, it is just an overview. You perhaps also did some potential flow analysis and all. So that is part and parcel of dynamics of inviscid flows. So by and large, this is in a nutshell. If you say, if in a single slide I was to do this review, perhaps I could have done it in this manner only. So I hope you will accept that as a quick review of Fluid Mechanics 1. Now we move on to how we will be extending this in the course, present course, Fluid Mechanics 2. Right, so now in Fluid Mechanics 2, we start the course with the first module, which will be taken up by myself. So my lectures would span these broad topics. The first thing is that I will be extending the ideas in kinematics, which is again an important aspect of the development of mathematical model of dynamics of viscous flows. You have done dynamics of inviscid flows in the earlier course, but the know-how to incorporate the viscous effects in a general way are still not known. So we will be the main contribution coming out of this portion of the syllabus would be you will be able to incorporate the viscous forces acting on a fluid particle in a very general way, and therefore you can talk of dynamics of viscous flows once you have gone through this segment of the syllabus, which we are calling as module 1. So in the kinematics there will be an extension and the extension of knowledge in terms of learning to express and understand strain rates at a point. And I'm talking of all types of strain rates: longitudinal, shear, volumetric. So, in a general way, how do we write these strain rates at a point in a fluid? And what is the interpretation? What is the physical interpretation of these? How do you conceptualize? How do you visualize these strain rates at a point? From physical point of view, all that will be part and parcel of this treatment. And then there's a concept of fluid particle rotation, which is connected to a property known as vorticity. So we will try to precisely pinpoint the physical conception of vorticity. That is, we will be very precisely defining it in terms of rotation rates at a particular point in a flow domain. So you will be knowing what exactly is vorticity, and not just in terms of a mathematical definition, but more a physical feel to it. And then, of course, you have to talk of certain tensors in fluid mechanics. Tensors you will learn. In fact, we have a whole handout of algebra and calculus of scalars, vectors, and tensor functions that is available on my homepage, faculty homepage. You will also be downloading it and keeping it as a ready reference. So tensors are very important. You deal with tensors in all kinds of continuum mechanics courses, even in solid mechanics also. So velocity gradient tensor. So this is a specific tensor related to kinematic aspects. So we will be talking of this velocity gradient tensor, and we will show you how you can use this tensor effectively to eventually obtain the strain rates and vorticity in a very general way for any kind of coordinate system that you are intending to use. Then governing equations, of course, they are the main players. So mass conservation, momentum equation, and of course the equations need to be supplemented with proper boundary conditions. Boundary conditions at this moment you can think of them as typical conditions at fluid interfaces with other types of media like solids, like gases, even some other immiscible fluid. So when one fluid is being considered, then unless if it's a liquid, then it can have two types of interfaces. Either it can, three types rather. A liquid can be having an interface with a solid, it can be having an interface with a gas, it can be having an interface with another liquid which is not miscible. And if you have a gas which is also a fluid, then gas obviously can have only two interfaces, either with a liquid or a solid, because there won't be any gas-gas interface. So interface conditions are there, which we will talk about them in detail, and they play a role in sort of constraining the fluid motions. So in fact, if I were to tell you that the basic equations are the same for all fluid flows, but yet when we look at different fluid flows, either in nature or in technological environments, they are all different. So what makes it different? These are precisely the boundary conditions that makes the flows different from each other. So we will be having a discussion on that. Then there is another very interesting point, kind of a concept of dimensionless formulation, and which leads to the natural consequence is the dynamic similarity. So here we talk of two different flows which may be geometrically similar. So what may be the conditions under which the flows themselves will be dynamically similar? These are the questions that will be addressed in this in these section of the syllabus: dimensionless formulations and dynamic similarity. These are very important from the point of view of model testing, okay, in case of fluids. So for example, if a car is being designed, or any other any other such system is designed, and you want to study the aerodynamics around the car, then one option is to actually make the car and run it on the road and take a lot of readings of flow pressures and flow velocities around it. So, but that testing, which we call as the actual real life testing, is one possibility. The other possibility where you can have more control over the conditions is to test a smaller sized version of the model of the car, and test it in a typical laboratory conditions. So then the natural question arises that the conditions in the laboratory should be such that the actual real flow and the flow in the lab around the small model of the car should be in some way connected and dynamically similar. Otherwise, the whole exercise would be meaningless. So such kind of routine testing in the labs is supported by dynamic similarity conditions, and the knowledge of all that comes from dimensionless formulations. Then myself, I will be signing off with the last section, which I call it as exact solutions. My module will be ending here, and in exact solutions, these are what we were discussing in the objectives as classical problems whose solutions teach us two things. One is how the viscous flow behaves, and the other is the mathematical skills of approximation and analysis, which can lead to analytical solutions. This skill is developed through these exact solutions. So exact solutions are the point where we test all our knowledge that we have learned above, and apply it for the solution of some relatively simple geometrical problems in viscous fluid flows. So these are typically, from the student point of view, these are the areas where he will be doing the problems and numericals and analysis type questions. This is the section of exact solutions where he is expected to apply the knowledge of dynamics of viscous flows. And so this is where the module 1 ends, and the module 2 begins, which is as I pointed out in my objective, one of the objectives is to look at an important phenomena known as boundary layer phenomena. So module 2 starts with boundary layer equations and their characteristics, boundary layer characteristics, and then moving on to the separation of boundary layers. What is the separation, how we can understand separation from the boundary layer characteristics, and how we can control it. Then there are some specific case studies regarding the self-similar solutions of boundary layers. So so we then towards the end we have an introduction to turbulent flows, and in turbulent flows we will be specifically just giving you a very basic and introductory ideas of characteristics of turbulent flows. What is the concept of length and time scales in these flows. You may not appreciate, that's why I'm moving fast at this on this slide, because this is just to give you an idea what is in module 2, and the statistical approach for turbulent flows, and finally we'll end uh, on mean flow equations and closure problem. So this slide is more or less just trying to tell you that a lot of new knowledge is in store for you if you compare it with what you learned in fluid mechanics 1. That's the only idea. Of course, when we will be actually going through the course, then you will be appreciating these topics. So moving on quickly to conclude this introductory lecture. Now to conclude this introductory lecture, we will go through quickly the texts or the books that we advise for this course, and some supplementary study materials. The first and the foremost topping the list are the lecture notes that you will be getting from our side in PDF format. Those will be detailed lecture notes. Of course, they will be supported with some PowerPoint lectures where I'll be more explicit in terms of using diagrams and simplified figures and sketches to help you understand those lecture notes. So they are the foremost study material that you will have, the top priority study material that we can provide you. And then the textbooks follow. The Viscous Fluid Flow by F.M. White, McGraw-Hill 3rd edition. This is a book usually provided by the library to each one of you, and there are some more excellent texts like Fluid Mechanics by Kundu and Cohen, Academic Press 2008 4th edition. Then there is Incompressible Flow 3rd edition, Ronald L. Panton, Wiley India publishers. And for turbulent flows, though we have given this text by Jean Mathau and Julian Scott, An Introduction to Turbulent Flow, Cambridge University Press, but even introductory chapters in Viscous Fluid Flow by F.M. White, or even in Kundu, Cohen, or maybe Panton, they all contain a basic introduction on turbulent flows. So by and large, our lecture notes would be sufficient, but for those who want to go deeper, this book has been included here in this list on turbulent flows. Please note the supplementary material, because these are two very good mathematical aids. We call them as mathematical aids because they contain in very precise manner the various mathematical tools that they will be invaluable tools in this course. So and I will specifically discuss them in my talks or lectures also, and you will find as you move on in this course, as you become familiar with these mathematical tools, they are really very useful in writing the fluid flow equations, particularly for any kind of a coordinate system, not just fixing it to Cartesian or any specific type. So if you want to, and also retaining the essential physics in the equations. So these two links, these two aids, mathematical aids, they can be downloaded through links on my departmental homepage. They are available there. They are available in PDF format. You can download them and use them as important, you can say, tools helping you out with the various mathematical aspects of the course. So, thank you very much. I would conclude my first introductory talk with you, and after this, we will be formally starting this course. And so, thank you very much.